All right, so your first reaction here for our alcohols is called dehydration. In this reaction, all you're really going to do is pull a water out of our alcohol and create a double bond in its place. So it's actually similar to a reaction from last chapter. It was hydration last chapter, so I added a water across a double bond. But I'm just going to do the reverse here. So on this first example, I have a hydrogen on this carbon on the left, and I'm going to take that hydrogen along with this hydroxyl group to make a water. And in between those two carbons, I'm going to make a double bond. So my products here are going to be an ethene and a water, right? All I have to do is take a water out, create a double bond. Again, that should be very familiar because the last chapter we just did the reverse. We added the water across the double bond and ended up with the alcohol. Right, so should be pretty easy, but there are a few things that you need to know. Right, our next example here, right? I have options. I could take a hydrogen from this carbon on the right, or I could take a hydrogen from this carbon on the left. Now, same as last chapter. Sometimes you'll make two products, sometimes you won't. First thing you always look at is that molecule symmetrical? Because if it is, then it wouldn't really matter which one you take it from. And in this case, it is symmetrical. So whether I take that hydrogen from the left or the right doesn't really matter. I'm going to take this one from the right and the hydroxyl group to get my water. But if I put that double bond between this carbon and this carbon, it's going to be the same as if I put it between this carbon and the middle carbon, because I'm still going to end up with a 2-pentene either way, right? One's just flipped over. So that one, I'm only going to get one product because I have two options, but they're identical. The next one, though, I actually have three different options. Since I started with the tertiary alcohol here, I could take a hydrogen from this carbon, or from this carbon, or from this carbon to make my double bond. So these ones are probably going to be the hardest, the tertiary examples. Secondary, primary, I do have all classes up here. But in this case down here, right, since it's not symmetrical, some of those carbons are different than others. These two carbons are actually kind of identical because they both have 3 hydrogens on them. But this other carbon only has 2, so it's different than the other 2. I have to decide which carbon I'm going to take my hydrogen from. Right? Last chapter we would have used Markovnikov's rule to solve a problem like this, and we're still going to use Markovnikov's rule this chapter. The difference being we're just going to do the reverse. Right? Since this is the reverse reaction, the rule is also reversed. I'm not worried about which carbon has more hydrogens. Now I'm worried about which carbon has less hydrogens. Because as you can see over here, this carbon only has 2 hydrogens. That's the carbon that I'm going to take a hydrogen from. So say this hydrogen here in the hydroxyl group, again, I need to make a water, but that forces me to make a certain product that would look like this, right? So I'm going to put a double bond between that second and third carbon in my chain, and that's going to be my product. As opposed to, it would have been possible to make this product, right? Or maybe I would have put the double bond here, but either way it would have been the same. Right? But Markovnikov's rule keeps me from forming that one. That's not actually going to be my product. Right? I always steal from whatever carbon has fewer hydrogens to begin with. Right? These 2 carbons have 3 hydrogens. The other one had 2. So I have to steal from the one with 2. That limits me to 1 product here, and I still have that water byproduct. So Markovnikov's rule is still going to be in play. You just have to flip it around. At last chapter, it was whichever carbon had more hydrogens. This time you're looking for the one with fewer hydrogens. All right, so hopefully that's good.